One of them is this idea of cuckoo hashing. But the other, and the way that I want to study this cuckoo hashing business, is through a technique that I really like, which are called encoding arguments. And these are ways of doing probability without doing too much probability. And I like that because I find it's a way for people like us, computer scientists who think constructively, to prove some sort of difficult probabilistic results by coming up with algorithms, or more specifically, coming up with clever encoding algorithms. So first, we'll start with just the background we need for this. So, let's say I have a set U, and a code is a function that takes elements in the set that I'm trying to encode and maps them to bit strings. And it has to have one property, which is that it should be injective. Okay. So I have the set U that I'm trying to encode. I have the set of all bit strings of any length. And I have a function C, which takes each element of U and maps it onto a bit string. And injective, you might have also seen the name one-to-one, just means that if I take two different values in U, they go to two different bit strings. Right? So you can just think of this as a binary encoding for the elements of U. Key point is not every element in U has to have a code that's the same length. And I'm particularly interested in prefix-free codes. And what are those? So prefix-free code is when I take any two elements of U to different elements and look at their codes, then it should not be the case that I see something like X's code is of some length, let's say 4, shorter than or the same length as Y's, and Y's code starts with X's code. Okay. So that is not something I want to see in a prefix-free code. So this code word for X would be a prefix of the code word for Y. That's not allowed. Okay. Good. All right. So here's something silly, or an observation. And what I like about this technique is actually it's all sort of easy observations that somehow lead to proofs of rather difficult statements. Observation, which is the number of X's in the universe, so the number of things that I want to encode, such that the length of their code word is less than or equal to L, is at most 2 to the L. Okay. And that's very easy to see. So this is for prefix-free codes. Okay, so that's very easy to see. So the way to do that is to say, what we're trying to count here is the number of things over here which give you a code word whose length is less than or equal to L. The less than or equal to is annoying. So for each of those things whose length is less than or equal to L, let's pretend that I'm interested in L is 6 here. I will just pad it out with extra zeros so that its length is exactly L. And when I do that, I'm still going to get something which is injective. So I still won't have two things going to the same code word. And the reason for that is that the original code before I did this padding was prefix free. So for instance, I will never see somewhere else something like this, because that would have meant that the original code was not prefix free. Okay? So after I do this padding, I still get something that's injective. So that means I have a one-to-one-to function from U onto these bit strings. Some of the elements of U go to bit strings of length exactly L, and some of them go to bit strings of length bigger than L. Well, the number of bit strings of length exactly L is only 2 to the L. And everything which used to go to a bit string of length less than or equal to L now goes to a bit string of length exactly L. So there's at most 2 to the L of those things. All right. Good. And here's another trivial observation, but with a fancy name. So for any code, let's say prefix-free code, pick a random, let's say X in the universe, then the probability that the length of X's code word is less than or equal to log of the size of the universe minus S is less than or equal to 1 over 2 to the S. Okay. Why is that? Well, we have this observation. The number of code words of this length here is not more than 2 to the log size of U minus S. So the number of things that I could pick from U which would give me a code word that short is at most this, but the number of things that I can pick from U, and I'm picking randomly from U, uniformly at random, well, that's just the size of U, and 2 to the log U is just the size of U, so what I'm left with is 2 to the minus S, which is this probability here, okay? So this is an extremely powerful thing. So really, in basic probability, it's very, I mean, it takes a while till you start to get probabilities that are this small for somehow complicated things. Usually there's some advanced technique necessary. Nothing fancy is needed here. Okay. So let's put that aside. The uniform encoding lemma, the probability that the length of the code word for random x is less than or equal to log of u minus s is less than or equal to 2 to the minus s. Okay. So one interpretation of this is log of u, that's the number of bits you would need in the most obvious code for s, where everybody just gets a different log u bit integer. So that's sort of the basic thing that you can do, at least when the size of u is a power of 2. And this thing basically says if you want to save, if you're hoping to save even a little bit off that, the chances of that happening drop very quickly, exponentially in the savings. So if you want to save even 1 bit, the probability that you can do that is at most 1/2. Another way to say that is at most half of the elements in here can have a code which is 1 bit less than the log u. Okay. All right. And I'm not going to be fussy here with floors and ceilings. When I take logs of integers, I'll just assume that they're integers. In fact, you can, there's a formal justification for this, but I definitely don't want to get into that today. Okay, good. That's the tool that we're going to use. And we're going to use it to study cuckoo hashing. So what's cuckoo hashing? Here's the setup. We have a set x1 to xn of things we want to store. I won't be too much more specific than that because we're actually going to use cuckoo hashing to do 2 different kinds of things, both of which are storing sets or dictionaries, but they use slightly different aspects of this thing. So for now, let's just fix the set of things we want to store. It's n elements. Okay, we're going to use 2 tables, 2 arrays. Let's call them T0 and T1, each of length m, which is at least 2n. So here's the picture you have. T0, T1, and we're going to use 2 completely random hash functions, H0 and H1. Okay. What does that mean, this completely random business? This means that H0 of x is a uniform over these possible number of m table rows here. And the same thing with H1 of x. And that's for any x Well, for any x that we might be interested in storing this table, in particular for any of these x's. Okay, it's a very strong assumption about these hash functions. And all right, so good. And sometimes we may even want to pick new hash functions that have the same property. So again, a super strong assumption. But if we, well, over here, we'll make a picture of what that looks like. So we can make this sort of table. That these functions, these two functions we have, they fill out this table, right? So at this location, I would write whatever the value is of h0 of x1. And here's h1 of x1. Here's h0 of x2. Here's h1 of x2. And so on. Now, this is a table with n rows, 2 columns, and the entries here, these are integers in the set 1 through m. Okay. So the number of these things, so our universe, the thing that's going to be the random experiment that we're going to be doing, so whenever we talk about probabilities, it's going to be over a random choice of this thing. It's going to be a random choice of this table, the entries in this table. Okay. So how many possible such tables are there? Well, we have m choices for each table entry, and we have 2n table entries. Okay. Is that clear? So that's the size of the universe. That's the number of possible pairs of hash functions we can have, or at least for these things here. Okay. So we'll write that down. Size of u is m to the 2n. And then, since we're going to be using it a few times, log the size of u is then 2n log of m. And it's not by accident that we picked m to be bigger than or equal to 2n. The reason we want that is because then a log of m is bigger than or equal to log of n plus 1. Or another way of saying that is log of n is less than or equal to log of m minus 1. So we're going to be working on functions that encode this table efficiently. So the way we're going to prove that certain events have a low probability of happening is we'll say if those events happen, well, we'll make a code and then say if one of those events happens, then the length of the code word that I get is significantly shorter than this. Good. So this gives rise to a thing that we call the Cuckoo graph, which is this bipartite graph. And I'll stop drawing it with boxes like this, and mostly I'll draw it the way we normally draw graphs. with nodes where you have an edge called x1 that joins h0 of x1 and h1 of x1, h0 of x1 on the left side, h1 of x1 on the right side. Okay. So h0 is an index into table 0, h1 is an index into table 1. Okay. And same thing for, for every xi, there's an edge called xi that joins these with these two endpoints, h0 of xi and h1 of xi. All right, this thing here I will call the Cuckoo graph. And where the name Cuckoo comes from will become apparent in a little bit. All right. So I think the best place for us to start is by considering some properties of the Cuckoo graph, proving some things about this Cuckoo graph. So and I should point out that it's a multigraph because there's no reason to think that, or it's not impossible that we have some xi with these two endpoints and we have some xj with the same two endpoints. That just means that when we chose this table here, we happen to get the same row appearing twice, the same two values appearing in two different rows, the row for I and the row for j. And well, that happens with some probability because, well, there are lots of tables out of the m to the 2 to the n that we choose from where that happens to be the case. Okay. So let's ask what sounds like a simple question. Well, let me just recall that the Cuckoo graph is bipartite. What does that mean? Well, that means that any cycle has even length. And why is that the case? Well, a cycle is it's like a path, so it's a walk in the graph that begins and ends at the same vertex and doesn't, other than that, doesn't have any repeated vertices. So that means a cycle, has to start on one side or the other. So let's call this the start of the cycle. Well, that means it has to end where it started. And now you can just see that, well, because the graph is bipartite, it only has edges from one side to the other. Each step takes you from one side to the other. And so the length of the cycle, you have to do an even number of steps to finish off where you start. So here's a question, or the probability that the Cuckoo graph contains a cycle. Any ideas? You think it's likely that it contains a cycle? Unlikely? Happens with a reasonable chance? Okay, so unlikely, maybe likely. Well, so here's an argument for maybe why it's likely. The birthday paradox is an argument for why it's likely, because we have each row here is two random values between 1 and m. So there's m squared possible rows. And as soon as we get two rows that are the same, we have a cycle. I mean, that's one way to get a cycle. It's a super short length 2 cycle. And we know from the birthday paradox that they start to become kind of those equal birthdays become kind of likely when the number of people, that's the number of rows, is about the square root of the number of days in the year. And that's the regime we're in here, right? Because m squared is about, m squared is about n squared with up to a factor of 4. So, so the birthday paradox says seems reasonable, and that's only counting cycles of length 2. If you want to do, now if you wanted to prove this using the sort of standard tools of probability, this is not an easy problem. Because first you have to figure out what's the probability that you have cycles of length 2, and then what's the probability that you have cycles of length 4, the probability that you have cycles of length 6, and it's not clear from the outset which way this is going to go. All right, and all right, so we're going to try and do this with an encoding argument. So it looks like we're going to say, we're going to try and find an encoding of this table which is somehow small when the graph has a cycle. Hopefully smaller than this, in which case we'll be able to say at least that that probability is smaller than 1. All right, so let's try that. So we're going to come up with a code for this, all the entries in this table that should be a little bit short when we have a cycle. So suppose yeah, we'll describe a code for yes, the entire table here. So we're in the setting of this uniform probability, uniform encoding lemma. We did pick something completely at random from the universe. We know its size, so we're looking at using this thing. Okay, so suppose the Cuckoo graph has a cycle of length 2a. So for example, there's a cycle of length 2 times 3 that might show up in our Cuckoo graph. All right. So I would like to somehow use this to make an efficient encoding. So here's what the code is going to look like for this Cuckoo graph. first thing I'm going to do is write down the code for A, the length of the cycle. And using something we've seen before, this alias code. What's the alias code? I'll write down the first few things because that's all we'll need. So x, alias of x. When x is 1, alias of x is 1. When x is 2, alias of x is 0, 1, 0. When x is 3, alias of x is 0, 1, 1. When x is 4, alias of x is 0, 0, 1, 0, 0. So it's just a bunch of zeros which tell you the number of bits to read for the actual encoding of the integer you're interested in. Okay. Minus 1. So when you see a 1 straight away, that's the code for 1. But when you see a 0, 1, that means starting from here, starting from this 1, that's the integer you're interested in. Okay. All right. So we're going to have that there. Now, the cycle has some vertices. Should be careful. xi1, xi2, so it has some edges, and remember each edge of our Cuckoo graph corresponds to one of these things. The edge is defined by the 2 hash values of that thing. And it has vertices. What are those vertices? Those vertices are entries in our hash tables. So let's say that on the left hash table we'll call A, the right hash table we'll call B, or we'll just use these to distinguish them. So this is something like A, J1, B, J2. Let's be a bit more careful. J1, B, A, J3, B, J4, A, J. How did I do this? 2, 3, 4, and back to B, J5, and A, J6. Okay. So that's what the cycle looks like. I'll pick one of the edges that, I don't know, looks like this, let's say. It doesn't actually matter. So let's write down the next thing we're going to put in our code is the sequence I1, I2, I3 up to I2A. So that's these things on there that tells me what these edges correspond to. Next thing I'm going to write is J1, J2, and J3 up to J2A. And these are just going to be in normal binary. Well, how many bits is that? This is going to be these numbers here, these indices, they're coming from up here. So each one is an integer in the range 1 to n. So that is going to be 2a times log n bits. These ones are integers in the range 1 through m. So that's going to be 2a log m bits. This one we'll see in a little bit. We'll study it carefully in a second. But just if I give you these things now, let's go over to the table and see what we can deduce just from these things. Well, the first thing here is I1, which means I know something about this row xi1. And actually, I know what is in that row. There's a J2 and a J6, or sorry, a J1 and a J6, right? A J1 and a J6. And as long as I'm consistent about what, whether I start with I pick an edge that has an A on the left and a B on the right, then I'll know exactly what to do here, which is to put a J6 at this table entry and a J1 at this table entry. But I also know I2. So for xi2, maybe that's this one, I know to put a J1 and a J2. Okay. And so on. Okay. So what did I learn here? I was able to fill out 2A table entries just with what you've given me so far. Agreed? I don't know what's in the rest of the table yet. So then the rest of the code is every table entry we don't already know. So imagine you're the decoder, you already looked at these things and you filled out the table entries that you can deduce from those. And now the rest of the code is just the table entries you don't know yet, I don't know, left to right, top to bottom. So you read them off and fill out the rest of the table. Okay. So there's definitely everything we need here to decode this, to encode this whole table and to decode it at the other end. And the fact that we can decode it correctly means that this is a code that's injective. All right. So, so how long is this part of the code? This part of the code is, well, each table entry is 2 log m bits. And how many table entries are there? Well, there was n in total, but we already figured out a of them from what we got here. So this is n minus a. Okay, good. And the thing that I want to, that we're going to use here is this. Somehow it looks like things are going to even out. Whatever we saved up here, whatever we spent up here, we're going to save down here. So it looks like things are going smoothly. Either nothing won, nothing lost. But that's not true. And that's not true because log n and log m are not the same thing. In fact, this is less than 2a log m minus 2a. Okay. All right. So let's add up the length of that whole code word. So we've got this, which is at most 2a log m minus 2a. This is, sorry, this shouldn't be, yeah, this is 2a log m. And yeah, sorry, no. 2n minus 4a log m. Why minus 4a? Because there's 2a rows that we know. Each row has two entries in it. Okay, good. So if I add all of this up, then this plus this plus this, then I get what is it? 2n log m minus 2a. The minus 2a comes from here. But there's one little piece that I haven't added yet. That's this piece. Plus whatever it costs me to use the alias code for the value of a. And something that you can check from this table here is that the length of this alias code for any value of a is strictly less than 2a. And since it's an integer, that means it's less than or equal to 2a minus 1. In fact, this is where that's tight. The length of the alias code is right. The length of the alias code for 1 is 1, which is less than 2 times 1. Everywhere else just gets better than that. So that means that this thing is 2n log m minus 1, right? We have a minus 2a. We have this thing, which is not more than 2a minus 1. So we're left with a minus 1. So if the graph contains a cycle, this encoding will use 1 less bit than this number. It may use even less than that. In fact, the longer the cycle is, the more bits it saves. Because usually the difference between 2a and the length of the alias code for a is huge. If a is big, right, this looks like 2 log a, and this is 2a. The only place it's even close is right here when a is 1, which actually corresponds to some intuition that actually if we get a cycle, the most likely kind of cycle is one of length 2, just where 2 different xi's happen to choose the same 2 hash functions. The cycles of length 4 are already getting less and less likely. Okay, so that's the code length if we get a cycle of length a. So that means that this, well, here's the s in this this equation. It's a 1. So this is at most 1/2. So an incredibly complicated looking property of this Cuckoo graph an incredibly complicated looking property of this Cuckoo graph, we can get a good upper bound on it. And we didn't really do any probability. We just came up with a clever encoding scheme. Any questions?
Todd, I have a question.
Yep.
What happened to the 4A? I'm kind of lost in that one. In the last, like everything other
The 4A here?
Yeah.
Okay, so when I give you these 2A values of I and these 2A values of J, that means there are 2A rows in this table that I now know the values in them. That's 2A rows, but each row contains 2 values. So that's 4A values that I don't need to tell you down here.
Sorry, my question is in the code length. We did not include the 4A. Like I see the other parts, the line at the very top of the.
Oh, the 4A comes from when you add these things up. This 4A log M cancels out this 2A log M and this 2A log M.
Oh, okay. Thank you.
So you're left with the savings of minus 2A plus whatever the length of the Elias code is.
Okay, now I see it. Thank you.
Good. All right. So write that down. Probability that we get a cycle is less than or equal to 1/2. What's that? This Elias code is prefix free, yes. Elias code is prefix free. The rest is binary coding with fixed length codes. And you know, right, the reason that I tell you A in Elias code is so then you know the next 2A log n bits are the values of the i's. The 2A log m bits after that are the values of the j's. And then after that comes everything in the table left to right. Okay. So that this code is prefix free by the fact that there exists this decoding algorithm that can decode it and know when it's over, right? From this value that you get from the Elias code, which is prefix free, you know exactly what the structure of the rest is and when to stop. Okay. All right, that is frankly amazing that you can do that without any major counting. Right, if you tried to do this with straight probability, you end up having to count the number of cycles of length 2A, using a union bound over those things, and checking the probability that each of all the edges of each such cycle exists, and having to sum that up over all possible lengths of the cycles. It's horrible. Okay, good. Let's look at another question. What is the probability that the Cuckoo graph contains a set of A vertices, or let's not call it a set, let's say a subgraph with A vertices and A plus 1 edges. So another way of saying that, what's the probability that I can find in my graph a set of A vertices with more than A edges between them? Okay, so we'll try and figure out what the answer is we should put here by coming up with our encoding scheme again and seeing how much we can save in this case. All right. So a subgraph with A vertices and A plus 1 edges. So if you have a subgraph with A vertices and A edges, that's what's called a unicyclic graph. And those are graphs that look like lollipops, possibly without the tail. So a cycle has the same number of vertices and edges. That's what we were just studying. But another kind of subgraph like that is a cycle with a little tail on it. But now if I have more vertices than edges, or sorry, one more edge than vertices, and there's sort of only two kinds of graphs you can get this way, and they look like this. The dumbbell or the theta. Okay. All right. So let's look at these two graphs and see what we could do with them. So if I have a graph like this, I can take away two edges. Just pretend they're not there for a moment. Let's say this one and this one. And now my graph is a path that starts here and ends here. And if I have this graph, I can take away this edge. So it starts here and this edge. And now my graph is a path that, say, starts here and ends here. Yep. Yeah. So, for instance, here's the version of this graph with only two vertices. And indeed, if I take away two edges, then I am left with a path that contains all the vertices. So this captures all of those cases, but you need to convince yourself that that's true. Okay, so let's see what we can do to encode these things. So what are these things then? Well, this thing here, in either case, after removing these two edges, I have a path with, what are those? A vertices and A minus 1 edges. Right, every path with A vertices has A minus 1 edges. That's just the number of edges in those things. Plus these two other things. Plus two extra edges adjacent to the endpoints. Right, so at the start of this path, there's an edge that I deleted, and at the end of this path, there's an edge that I deleted that goes back into somewhere else in the path. And the same thing happens here. The start of the path has an edge that comes before it, and the same at the end of the path. All right, so I can tell you all of this stuff. I need to tell you the A vertices of the path. that takes A times log M. Remember, the vertices here are entries in the table. So they're indices into the two tables, left or right. A minus 1 edges of the path, that is A log n minus log n. Right, each edge corresponds to one of those xi's for I and 1 to n. So this is just A minus 1 times log n. That's those things. Now I want to finish this thing up and tell you the last two edges. Okay. And let's call those edges E1 and E2. So I need to tell you E1 and E2. So those, again, those are xi's, so for I between 1 and n. So that's going to be 2 log n. But, so, and I know E1 is adjacent to the first vertex I specified in the path, and E2 is adjacent to the last vertex I specified in the path. What I don't know yet is where, so if you're blind and you're just reading this, here is what you see. I know everything along here. I know everything about this path. I know what the labels are on these two edges, but I do not know yet where they come back and connect into this graph. Right? So in this picture, you can see it, but if all I've told you is this, then all you know is, yes, this E1 comes back and connects somewhere in here, and so does this E2. I need to tell you where. So the other endpoints of E1 and E2. How many bits does that take? Well, normally that would be 2 log m, 2 log m, right? Because those endpoints are integers between 1 and m. But there's an easier way for me to tell them to you, which is just to tell you the index in this path now. There's only A vertices in this path, which could be much less than m. And I know these other things connect to something in this path, something that I've already told you. So that's only going to be 2 log A. And then I should not forget to make this prefix free. At the beginning, I need to tell you the alias code for the value of A, the size of this graph. All right, so what have I learned after all of this? Well, from all of this, I have this graph with A plus 1, A vertices, yeah, A plus 1 edges. This was A vertices, A plus 1 edges. And now I know everything about that, which means that I know A plus 1 rows of this table. And now everything else, which is n minus A plus 1. That's the number of rows of the table that I don't know yet. And each row takes 2 log m bits to specify. All right. And if you add all of this up, you will get 2n log m minus log n coming from here plus the Elias code plus what we had here, 2 log a. And there should also be, yeah, this thing, that's the minus log n. And this is an a log n, so there's a minus a. Right, this is an a log n, not an a log m. So this is a log m minus a. So if you carefully add all of this up, you get the number you're expecting minus a log n plus all this mess. And what is all this mess? This looks like a minus a plus an o of log a. Well, except for small values of a, this is a negative number. And for small values of a, well, it's at most some constant. So when you, so when the point is, no matter what the value of a is, this thing is 2 log is at most 2n log m minus log n plus a constant at most. Which then, if you apply this thing, that means the probability that this happens, this is your S. So you get 2 to the minus log n plus O of 1 is equal to O of 1 over n. Okay. So this is quite unlikely to happen. As n gets big, it's really not likely to happen at all. Again, an extremely complex property of this graph that we were able to study just with this encoding argument. Try and do this with straight probability. It will be a major struggle. And even if that's your goal, ultimately to do that, actually, even these encoding arguments give you a clue on how you're going to do that. The same way that the encoding argument for cycles basically pointed us out to the fact that the most likely cycle is a cycle of length 2. This one is telling us that because we have this plus O of log A minus A, that the small values of A are going to be the problems. So stupid things like 2 vertices with 3 edges between them. Those are going to be the most common things. So if you were going to do this by counting using the usual types of probability, you're kind of figuring out that as the graph gets bigger, that it's becoming much and much less likely that these things occur. In fact, exponentially less likely. So your counting just has to be careful for the small graphs. Okay, good. So probability of a dumbbell or a theta is less than or equal to 1 over n. And finally, what I would like to look at is the following. I'm going to fix some value of I and ask about the probability that the Cuckoo graph contains a path of length k that starts at a sub h0 of xi or b sub h0 of xi. Okay. So I'm focusing on a particular xi here, and I'm worried about a long path that starts over here or a long path that starts over here. Those are the things that concern me. Okay, and path of length k. So you can guess that we're just going to do the same thing. We're going to specify whether it's at whether case A or B. And by case A, I mean it starts over here on this side. Case B, I mean it starts over here on this side. That's just one bit. Then I'm going to give the k plus 1 vertices on the path. And then give you the k edges on the path. And then everything else.
But I have a question.
Yep.
Shouldn't be the h1 of x1, not h0? Or did I misunderstand that?
Oh, you're right. h1 of xi. Yeah. Okay. The key thing here, which is a little bit strange in this proof, so it goes like the other ones. After I've given you all this stuff, I now know the two hash values for this xi1, the two hash values for xi2, the two hash values for xi3, and I know one more thing. I know the one hash value for xi. Okay. So in terms of this table here, this gives me a rows plus a half row. I know one of the entries in the row xi. And now you add all of this up. So that means this everything else here is actually going to be, what is it? N minus 2k minus 1 times log m. Sum everything up and you'll get 2n log m minus k. Okay. And so then that probability is less than or equal to 2 to the minus k. Good. So far we haven't done any data structures. We've only looked at analyzing this graph, but now we're basically done. All right, so how do you use this as a data structure? And why is it called a Cuckoo table? Or Cuckoo, why is it called Cuckoo hashing? So I take the elements x1 through xn, and I insert them into the table one at a time. When I want to insert xi, there's two places it can go. Over here in table T0 or over here in table T1. Actually, I'm going to stick xi here, no matter what. So xi is going to go here. What's the danger? The danger is that there was something already there. So there may have been another thing already there, in which case it's not game over, because the thing that's already there has another option, another place to live. So if there was a thing already there, let's say that thing was called xi1, well, over in the left table, it wants to live here. Over on the right table, it wants to live somewhere. So like the cuckoo bird, which is famous, although it's probably not true, for not making its own nests, cuckoo birds, I don't know, story goes, I'm not a bird doctor. Instead of making their own nest, they just find an existing nest, kick the eggs out that are in that nest, and they take it over. So if this cuckoo finds an egg in this nest, it kicks it out, and it has to go find another place. So this one moves over to here, which, great, if this is empty, you can stop, but maybe there was something already there. In which case, that's okay. That thing that was already there comes back and takes the spot on this side. Okay. And you go that way for a while. So first thing you might want to know is, well, what's the, what's just the expected time to do this? Well, there's a few things to look out for, but there's sort of two things that can go wrong. One of them is a really bad thing, which I won't talk about now, but the typical thing is, yeah, here's xi. It starts here, and then there's a sequence of things that get kicked out until it ends. And when does that end cleanly without any problems? Well, that ends cleanly when there's a path here of length k. It'll end after k steps. And if there's a path here of length 0, meaning there was nothing here before, it ends after 0 steps. And we know now the probability that there is a path of length k that starts exactly here is only 1 over 2 to the k. So from that, you can get that the expected time to do this, when half the time xi finds its spot for free, quarter of the time it has to kick one thing out, which finds its spot, an eighth of the time two things get moved. So that's one sort of thing to look at. Now the other danger is that, well, maybe there's a loop here and things just keep getting moved around forever. How does that happen? Well, what would it mean if things keep moving around forever? Things move around forever if you're trying to store more things than you have space for, right? If you don't have that, if there's enough space for the things you want to store, then eventually this somehow will find the space. But what does it mean to be trying to store more things than you have space for? Well, that means that the cuckoo graph contains a graph with more edges, a subgraph with more edges than vertices. Each edge is a thing you're trying to store. Each vertex is a place you're allowed to store something. But that's very unlikely. That's only with probability of 1 over n. In fact, that's not likely to happen at all in this process. Okay, so that's cuckoo hashing. That's how it works. The insertion time is expected constant. Occasionally, you get an unlucky situation where you have this kind of thing, and you have to pick new hash functions. And occasionally, you get maybe a very long path of length log n. But again, even that only happens with probability about 1 over n. So that's it for cuckoo hashing. The other thing I want to just talk super quickly about, and the reason that I wanted to talk about the probability of a cycle, is there's this cool thing called read-only dictionaries or retrieve-only dictionaries. And for those x1, oh, sorry, and searching in a cuckoo graph is easy. In a cuckoo hash table is easy. When I want to look for x, I compute h0 of x, I see if it's there. If not, I look for h1 of x and see if it's there. Those are the only two possibilities. So like perfect hashing, this takes constant time to do searches. Retrieve-only dictionaries, this is where you imagine x1 to xn are keys that store small values. Maybe d-bit values. Okay. So lots of possible keys, but each one only stores a small value associated with it. And I want something where I'm only going to ever search for keys that I know are in my data structure. So I don't have to worry about storing the keys, but I do need to store the values. And here's what you can do for that. So each of these things now is still of length m bigger than or equal to 2n, but the number of bits that you store here is only d, because each value that you want to store is only d bits wide. So this is like 4n times d bits, which could be way less than 4n log, well, who knows, however big this universe is, 4n log size of the universe. But how do you do it? Well, you store this so that the key associated with xi, I take t0 at h0 of xi, and I XOR it with t1 at h1 of xi. So the thing that I want to store with this, with xi, is will end up being stored as the XOR of these two things. That seems insane. How can that work? How can you guarantee that that works? Well, if you think about it for a little bit, you'll realize that as long as there are no cycles in the cuckoo graph, it's actually easy. For any component, you just pick the something in that component, put the value that you want to store there. So this would be, let's say, the data for xi. And then there's, some other thing that wants to, that there's some xi1 that also wants to use this. Well, now whatever I put here is just the XOR of the data for xi1 and this. And you just branch out this way, doing breadth first search. You'll never run into a problem because you'll never run into a cycle. So you'll never want to overwrite a value that you wrote previously. Okay, good. So that's it for today. I have to run now.